All right, let's look at an example of an application of a max and min problem in a multivariable function. A shipping company handles rectangular boxes, provided the sum of the length, width, and height does not exceed 96 inches. Find the dimensions of the box that meets this condition and has the largest volume. So you might remember these from Calc 1, max and min problems. The first thing to look at is what is it that you're trying to maximize or minimize. So here we're trying to maximize the volume, so we need to write a formula for volume. And so if we have a box, we could call this the length, the width, and the height. If you need to pause the video and write this problem down, go ahead and do that. All right, so the volume is length times width times height. Now we also have a criteria that the sum of the length, width, and height does not exceed 96 inches. So we need the length plus the width plus the height to be less than or equal to 96. Some other criteria that we might want to make note of is, because this is a real world problem, the width is going to be greater than 0, the length is going to be greater than 0, the height is going to be greater than 0. So we have this box. All right, so far so good. Now, if we're going to maximize the volume, then we're going to want the length, width, and height to be equal to 96. I mean, if you think you can maximize it with a sum less than 96, just think about you'd add something else to the length, width, and height to get it to equal 96. The volume's going to get bigger. All right, so now what we want to do is we want to take this volume formula. This is the formula that we're trying to maximize, and it would be great to get rid of one of these variables. So we can take any of these variables over here. It doesn't matter in this other equation, and solve for them. Let's solve for height. Again, it doesn't matter. But I can solve that for height and then come over here and plug this in over here. And so now I'll have volume as just a function of length and width. So that'll be length times width times height. All right, and so now what we want to do is we want to maximize this. So we want to find the maximum value. So in order to do that, the first thing we need to do is find our critical points, which we should be pretty good at. So if you want to pause the video and find the critical points and fast forward, that'd be good practice. But I will go through it here as well. All right, before I find my critical points, I think I'm going to rewrite my volume with this distributed. I think that's going to be easier to do the partial derivatives this way. Okay, so the partial of v with respect to L at LW is going to be 96W minus, let's see, 2. I'll put the W in front. Actually, let's keep them in order, alphabetical order. 2LW minus W squared. All right, and then we have the partial with respect to W, and that's going to be 96L minus L squared minus 2LW. All right, so remember, if we have a critical point, that means that we need both of these to be equal to 0. Okay, so I noticed that both of these have a factor. The first one has a factor of W, and the second one has a factor of L. So I'm going to go ahead and factor those out. So for the first equation, let's see, we'll factor out a W, and we'll get 96 minus 2L minus W equals 0. And the second equation, I'll factor out an L. Okay, so if I'm going to solve this, one solution would be that W equals 0, but that's not really going to work for us, is it? Because that would mean the width would equal 0. So the other option would be that 96 minus 2L minus W equals 0. Same idea over here, right? This L could equal 0, but that's not what we're going to need. We can't have a length of 0 in our box, so we have that. All right, so now with these two guys here, these two equations, we have a system of linear equations, so that should be something we know how to do. Maybe use substitution and solve it. Let's see. How about we move the L to the other side of this and then substitute this guy over here. However, you maybe you solve this for W and moved it over. Whatever. Okay, so we get 96 minus 2 times 96 minus 2W minus W equals 0. All right, let's see what we get. Minus 4W, oh, plus 4W. There, that's where we make those little mistakes, right? Okay, so that's 3W, and if we get negative 96, move that to the other side. What do we get? 32. Okay, so now let's take the 32 and we'll plug it back in over here to figure out what L is. Now we get 96 minus 64, so we get 32 as well. Okay, so that is our critical point, 32, 32. Now, we have a pretty good idea this is a maximum. This is what's going to maximize the volume. It's probably not going to get a minimum here, right? Let's go back up and look at our picture. If L is 32, and W is 32, then the height would have to add with this to be 96, right? Because L plus W plus H equals 96, so that's another 32. So it's a cube. So that adds to 96. So this would give us a volume of 32 cubed. That's not going to be a minimum, is it? That's not going to be the minimum volume. The minimum volume would be some flat, squished box with a little tiny height. Something like that. Okay, so I have a pretty good idea. This is my maximum value here. But just for kicks, let's go through that verification process. Okay, so that means we need to find our second derivatives, right? And VLL. Let's do those first and see how much room we have. Can I get these on the same screen? There we go. Okay, so so this guy with respect to W is just going to be negative 2L. And then this one with respect to L is going to be negative 2L. Okay, and then we could do WL. So look at our W1 and take it with respect to L. So that's going to give me 96 minus 2L. 96 minus 2L. Notice if I would have switched it and done this one with respect to W, I would have gotten 96 minus 2L as well. Okay, so now we do our little formula here. 32, 32. So we'll plug 32 into this one, multiplied by 32 into this one, subtract 96 minus 2 times 32 squared. All right, so this comes out to be, I already calculated this, 4,096 minus 1,024, which is greater than 0. And then now this is kind of interesting actually, because how do I know, in my other formula, we had to check fxx. It didn't really say to check fyy and see if that's greater than 0 or less than 0. So if I'm using L and W, how do I know which one is x and y? It's kind of an interesting question. Well, it turns out you could check either of these, and it wouldn't matter. So let's show that's true here. So if I check VWW at 32, 32, I get negative 64, which is less than 0, and certainly L is the same formula here. That won't always be true, but so we get negative 64, which is less than 0. So if you check your little chart, that's going to tell you that you have a maximum. All right, so the answer is, let's go back up here and see the question. Find the dimensions of the box that meet the condition and give the largest volume. Well, that would be 32 inches by 32 inches by 32 inches, and we could also calculate the volume of that as well.